The minimum thickness of wire used in domestic wiring must not be a size less than 1.12 mm in copper or 1.40 mm in aluminium in diameter. Those are the safety standard. However, I wonder, how thin can a wire get? I know it's a weird thing to think about. But, is there any limit? And we shall find it out in this video. Welcome to the realm of quantum wires. First, let's tackle the big question. What are quantum wires? Imagine a world where wires are no thicker than a few atoms, where electrons dance to the rhythm of quantum laws, and where the boundaries of classical physics blur into a realm of astonishing possibilities. Quantum wires are nanoscale structures that redefine the way we think about conductivity and electron behavior. Unlike traditional wires, which conduct electricity in 3 dimensions, these wires confine electron motion to just 1 dimension. Okay. This might help. Picture a traditional wire, electrons flow freely within its volume. Now, shrink that wire down to the nanoscale, and something remarkable happens. Electrons find themselves trapped within a slender path, restricted to move along a single direction. This confinement, called quantum confinement, leads to a phenomenon where electrons can only occupy specific energy levels. Think of it as electrons being forced to perform a quantum dance, following steps dictated by the wire's dimensions. These quantized energy levels are like rungs on a ladder. Electrons can occupy one rung at a time, and they must jump from one level to another. This discrete nature of energy states creates a breathtaking tapestry of quantum effects. But, why does this matter? Quantum wires exhibit extraordinary properties that open doors to groundbreaking applications in electronics, computing, and beyond. All of this is possible because of quantum confinement. Imagine electrons being confined to move in only 1 dimension within these ultra-thin wires. However, is the size of the wire, or rather the diameter, such an important factor for conductivity? Of all that I have learnt in middle school, reducing diameter will increase the resistance of the wire. Then how is this happening? Traditional wires follow classical physics rules, where electrons flow smoothly like water in a river. But quantum wires operate under a different set of laws. This confinement transforms electron behavior dramatically. Just like a guitar string that can only vibrate at certain frequencies, electrons in quantum wires can only occupy specific energy levels. These quantized energy states create a staircase of possibilities, a bit like musical notes on a keyboard, but for electrons. Traditional wires simply can't match this precision. They do not lack the staircases of energy levels that quantum wires offer, but are so zoomed out of the picture that their rough stairs are now smoothened. Think of it this way: if traditional wires are like a wide-open freeway, then quantum wires are like Elon Musk's Hyperloop. It is true that 2 electrons can't pass simultaneously, but the one that does can do without facing any resistance. Enough of theory. Let's talk about what can it be used for. Nanoelectronics advancements. Well, as the name already suggests, quantum wires offer a path to revolutionize electronics by enabling the creation of ultra-compact, high-performance components. Their unique energy levels can be finely tuned, leading to enhanced control over electron behavior. This precision opens the door to faster, smaller, and more energy-efficient devices. Quantum computing breakthroughs. They play a crucial role in the development of quantum bits, or qubits, the building blocks of quantum computers. The ability to confine electrons to specific energy states aids in creating stable qubits, paving the way for robust quantum computation. Photonics and optoelectronics. These wires are excellent candidates for light emission and detection. Quantum wires can serve as efficient sources of light for various applications, including lasers, LED displays, and other advanced optoelectronic systems. Sensors and detectors. They exhibit heightened sensitivity to changes in their environment, making them ideal for advanced sensor technologies. These wires can be integrated into ultra-sensitive detectors for applications such as detecting light, radiation, and even single molecules. Such sensors have potential implications in medical diagnostics, environmental monitoring, and security systems. Efficient solar energy conversion. Their tailored electronic properties can lead to improved light absorption and charge separation, enhancing the conversion of sunlight into electricity and leading to the development of more efficient and cost-effective solar energy solutions. Future quantum communication. By harnessing the quantum entanglement properties of confined electrons, these wires could contribute to the secure transmission of information over long distances, revolutionizing the field of secure communication. If they are such a revolutionary product, why aren't we making them? And, the bigger question is, can we actually make them? Or is it like graphene, we want to make it but it's next to impossible, as of now? As a matter of fact, we can and that too, in two ways. Creating quantum wires demands precision on the nanoscale. Two primary methods dominate this process. Top-down approach. Here, researchers start with a bulk material and use advanced lithography techniques to etch and shape it into the desired wire structure. This approach allows for precise control but can be intricate and time-consuming. Bottom-up approach. Hey, don't get ahead of yourself. It's not what you are thinking. This method involves building quantum wires, atom by atom, using techniques like molecular beam epitaxy or chemical vapor deposition. Ignore the jargon. All there is to this is it's incredibly precise and can produce wires with remarkable control over their properties. If it's possible to make, then what's stopping us from becoming a super advanced civilization? Size. Manipulating materials at the nanoscale requires extraordinary precision, often pushing the limits of available technology. Quantum interference. Quantum wires are highly sensitive to their environment, and even slightest interactions can disrupt their behavior. Shielding and controlling these interactions are a lot tougher than you think. Temperature control. They often need to be cooled to near absolute zero to exhibit their quantum properties. Achieving and maintaining these ultra-low temperatures can be a substantial hurdle and impractical in day-to-day use. Defects and impurities. Any deviations from perfection, such as impurities or defects in the wire's structure, can significantly impact its quantum behavior. Integration. No, it's not from the calculus class that you always hated. It means that combining quantum wires with other components to create functional devices poses a challenge to this day. Despite these challenges, researchers are relentless in their pursuit of mastering quantum wire fabrication, just like we invented the wheel. I know, it's not that easy. Learn more about the quantum world by clicking on this video.